Okay, congratulations, you found it. This is the lecture where I go through all the mass and energy forms in the universe, what they could be, particularly if they're perfect fluids. And if you don't know what that is, go see the Mass and Energy 1. So I am Robert Nemiroff, and this is Michigan Tech. And this is Extraordinary Concepts in Physics. And you can find us on YouTube, or you can find us on iTunes, or you can find us on the web here. So you can enjoy even if you're not part of this class. A lot of slides today, so this is a slide that I repeated from last time. So we're talking about solutions that are part of the standard Friedmann-Robertson-Walker part of the universe. Extrapolation of the universe is derived from general relativity. So after general relativity was derived by Einstein and published in 1915, Friedmann, Robertson, and Walker, among others, came up with a way of measuring time and space inside a universal component of that involved relatively few assumptions and allowed lots of extrapolations and predictions, and that became the Friedmann-Robertson-Walker metric of general relativity, GR. So that's where the hard work was done. This lecture is based on a summary of that goes through all the different energy conditions that you can find in the American Journal of Physics, published in 2008, by clicking on that link or copying that down. Okay, so we're going to go through the energy forms again. So possibly the strangest form and the most controversial form of energy is called phantom energy. So this has W, which is equal to pressure over rho. So this is energy density, and this is how much it pushes on things. This pushes on things in a negative way. This has in a gravitationally negative way. So it's if phantom energy exists in the universe, it will be everywhere in the universe. You can't hide from it. It's inside you and me. And its energy density is probably very, very small right now. But it could be increasing. And if it continues to increase, its pushing apart of everything around it will begin to dominate. And then we would explode as people. Other things would explode first. Our solar system would become unstable. The Earth would stop rotating around the sun because the amount of energy density, repulsive energy density inside the Earth's orbit would be greater than the sun's mass equivalent energy density, and so we would no longer feel an attraction toward the sun and we would go off. If this is true, and we'll go back this later, the universe would not end by just cooling off. It would end in a big rip where there's increasingly high energy everywhere in the universe. This is not yet excluded observationally right now. Astronomical observations, including supernovae and the microwave background, actually say this is a possibility, but it's not one that many people, not everyone takes seriously because it's controversial. Not only is it hard to account for how energy can act like this, but it just seems pretty weird. And so most astrophysicists prefer more tame forms of mass energy in the universe. And the one that was initially preferred by Einstein is the energy put into the cosmological constant. By the way, that last one was a dark energy, and this is a dark energy as well. The cosmological constant, again, fills all time and space, but it's constant. As the universe expands, the cosmological constant dark energy is always the same. So matter energy, like you and me, is diluting because galaxies are becoming further apart, one for every spatial dimension. But even though that happens, the cosmological constant, dark energy that pervades the universe, is always the same. Since the matter energy is going down right now, and the cosmological constant energy is remaining the same, we're becoming dominated by cosmological constant energy. This was first postulated by Einstein way back in the early days of general relativity because Einstein was worried the universe would have collapsed in on itself and he needed something to prop up the universe. And so he created a cosmological constant. Later, when Hubble realized through astronomical observations that the universe was expanding, Einstein said that was his biggest fault. It was then brought back any number of times by astronomers and physicists and cosmologists trying to understand quirks in the data. But it never really stuck until the 1990s when the supernova cosmology team found out that distant supernovae were dimmer than they thought they would have been if there was not some kind of cosmological constant energy. So since the 1990s, or the late 1990s actually, we now believe that there is a dominant part of the universe that fits well with a constant cosmological constant component. However, it is one of the research goals of modern astrophysics to explore whether the dark energy actually changes out in the universe or was much different early in the universe. And so we don't really know that there's a cosmological constant operating. We know it's some sort of dark energy. Okay, so here's one type of energy that isn't usually talked about, domain walls. These are sheets of energy that are repulsive. So if you were to go up to a domain wall, you'd say, oh, what's that? You'd have trouble going up the domain wall because it would repel you gravitationally. There are cosmologies where domain walls dominate the universe. This is a form of dark energy, so it could theoretically account for the universe expanding so rapidly. However, we don't see any. So we have telescopes, we look in every direction. Nothing looks to us like a domain wall. So maybe it's outside of our visible universe. The universe is huge. It extends further than we can see. Maybe there's lots of domain walls out there. Well, maybe. If you were to take a domain wall and wrap it into a ball, like this, it would look to you from far away like normal matter. If you were to take this domain ball and drop it on the Earth, it would fall at the same rate as a hammer or a feather, just like the equivalence principle says. It's only when you go close to a domain wall, which could have curvature on very large scales, that you see that it is actually something very different. If you go right up to it, you will feel a repulsive energy from it. The next thing, this is more popular in the literature, cosmic strings are the next form of mass energy that could exist in the universe that is a perfect fluid in the large sense. These are strings of energy. They're extremely thin. If they're actually slight, not necessarily tubes, but they do have a width. If you go right up to them, just like the domain wall has a width. If you go near a cosmic string, if you're a human, you will not feel either attraction to it or repulsion from it. They're gravitationally neutral. They could dominate the universe. Every now and then a paper is published saying we might think we see a cosmic string because they would create an unusual gravitational lens effect, which some people think they see. But then, so far, every time people have looked in detail, they can't convince themselves it really is a cosmic string. They might be lots of cosmic loops. They might be, many of them outside of our horizon that we can see, our visible universe. The density of cosmic strings, just like domain walls, would decrease as the universe expands. If you were to take a string and make it into a loop, if you had that power, and then you were to put it over the Earth, it would drop just like normal matter. It could be that cosmic strings are the same, have similarities to string theory. They could be similar. They could be the same, for all I know, for all many people know. They have the same equivalence principle as everything else. You drop them, they fall the same. If you go right up to one, though, one part of one, then you get strange effects. They would not attract you or repel you. These strings can actually have kinks in some way, and these kinks could be very luminous. These are other things that are looked for cosmic strings, which are not necessarily found out in the universe. They may have seeded galaxy formation in the early universe. That's also another theory. Normal matter, it's the stuff we're regularly used to. Pressure-free, W is equal to 0 because the pressure of normal matter is 0 compared to everything else. So this is the kind of stuff we used to think the universe was completely made out of. This is now not a dark matter. Now we're into the regular kinds of matter. Sometimes you can think of them as light matter. So protons, electrons, they're all this kind of normal matter. A normal matter is not moving fast with respect to the outside universe, which is why it has pressure of 0, W of 0. So this is non-relativistic matter, like the Earth is considered kind of normal matter, as is the sun. It's moving, but it's not moving fast enough. Only a small part of our universe is made up of normal matter, as we've seen. Next on the roll call is more normal matter stuff is radiation. So radiation actually has pressure. It is more gravitationally attractive than gravitation. It does dilute as the universe expands even faster than regular matter because early in the universe is like this, and then it becomes less energetic as the wavelength increases. Types of radiation are well known, like photons and neutrinos. Any W equals 0 particle, if you could move yourself fast compared to the microwave background, for instance, you would be considered a particle of radiation, not a particle of matter as concerns the universe. And if you and your fast friends were zipping around really fast, even though you're people, if you're moving fast enough, cosmologists would have to explain the expansion of the universe assuming you're radiation and not matter. Ultralight is a stable form of perfect fluid that might exist that's not discussed in the literature. I actually mentioned it in my article because I hadn't found it. It was a hole, it seemed to me, in the Friedmann equations. This dilutes faster than even radiation in the universe. It is not seemingly controversial because the magnitude of W is not greater than 1. All it has to be is greater than 1/3. I'll leave it there. There are no known examples. It might have been important in the very early universe because it might have diluted so fast that we don't see it now, but it might have been high enough to affect the very early universe. We don't know. Fields, which are different than perfect fluids, can mimic perfect fluids, but they don't necessarily have to. The simplest kind of field is what's called a scalar field, and it might have driven inflation. It also might be responsible for inertial mass and might be what's called part of the Higgs field that surrounds us. It's possible that the Higgs field that surrounds us could be a form of dark energy that would affect the evolution of the universe at some aspect. You can make more complicated fields, vector fields, and tensor fields, and they might even be right. But they're so complicated that we try to get away with scalar fields now and try to see how they evolve. It's possible for energy forms to change. For instance, if you were moving with your friends very fast as the universe expands, you would go from being radiation to being matter because you would eventually slow down as the universe expands. Curvature effects of strings and domain walls might unravel as the universe expands, so you could have some slow changes between energy forms. It's also possible to have fast changes when you have some kind of matter that decays. It then goes from normal matter and decays into radiation forms, fast-moving particles, so it's possible to convert quickly matter into radiation. That's possible. That's what I just said. So you can give a brief history of the universe this way. You can say that early on, before the Planck time, it seemed to us, so far as we know, that radiation was dominating the universe before then. So if you want to explain the expansion of the universe in the perfect fluid, you need to do radiation. Past that, there was an inflationary epoch where it seemed to be some kind of dark energy cosmological constant was operating. After that, after inflation ended, there was another radiation epoch, and W of 1/3 dominated for a while. After a while, the radiation diluted faster than the matter, so the matter took over and dominated the expansion of the universe, and we went into a matter-dominated epoch for a while. Now, in our modern epoch, the matter is diluting relative to an even smaller radiation cosmic constant that permeates the universe, and we're moving into a epoch of the universe that is again dominated by a W equal to -1 energy form. Jumping into the future, if the universe is dominated by phantom energy, we will undergo a big rip. It doesn't matter what the density is because a big rip, even if it's small, even if the phantom energy is really small today, it will grow to dominate the universe and rip us apart in the future. If, however, we are dominated by a cosmological constant, the universe will probably end in what's called a big freeze. Everything will just go far, far apart, will cool down to essentially nothing, and you will just have radiation floating about in the universe that even black holes will eventually evaporate. That radiation will eventually become very long wavelength and you'd have nothing left. Everything would frozen. However, it is possible to have a universe dense enough to undergo a big crunch so that the mass energy of the universe is enough to pull it back from expanding into contracting. Then everything will move toward each other. And when it moves toward each other, things again start heating up. You might get a bounce. You might get something we don't know. And if the end state of that, since we don't really know, can't go past that, it might bounce, but we call it a big crunch. Things crunch into each other, they heat up again. And that is the possible far futures of our universe, simplified in the most simplest terms we can. And there'll be more cosmology and other fun things, other lectures, and I will see you then. Bye.